So this is a presentation I gave a little while ago, December 2019. It's called Emulation and Other Stories. I hope you enjoy it. The slides are available on my website as slides, but this is a full presentation, and I've added some voice afterwards. So what this talk is about is we're going to try and show the various cheap and not so cheap ways in which you want to play, if you want to play with old technology. I'm a fan of old technology. I like playing with old computers, and so this is one way of doing it. Some ways are very expensive or almost impossible, and others are pretty cheap, and you can do it for very little money. Why do I do it? Well, because it's there, first of all. Obviously, it's something to do. It's fun, for some value of fun, you might say, depending on what your inclinations are. But I think it's fun to see the kinds of things we had to do years ago, and the amount of memory, the resources we had to do things. And so in that sense as well, it's educational, because people can find out what it used to be like, and see in a way how lucky we are today. Now, the main technology I'm going to be talking about is early mini computers made by one company, Digital Equipment Corporation, who were later acquired by Compaq, because they didn't really keep up with the times. And then Compaq in turn fell by the wayside quite quickly, and HP took them over. HP are not really interested in this stuff, and they've farmed off some of it to other companies in terms of rights. But they're still around. They still have some stuff on their website. So what I'm going to cover is, first of all, real hardware, and then replica hardware, building a replica, and then emulating the hardware in software. And hybrids of those. The hybrids are probably the most interesting. So the examples are, what are we going to do? We're going to look at some various machines. We're going to then look at what I call machination, which is playing with real hardware when you can still get it, and when you can afford it. If you're very rich, if I were very rich, I know which machine I'd go and get, but it needs three-phase power and a whole room to itself. That's a DEC System 10. Replication. What you do here is you actually construct a replica of the hardware. Sometimes you can do that using original chips that were used in the original machines, particularly in the later versions of those machines. You could use an FPGA, full programmable gate array, which is something which allows you to, in theory, build anything that you could build with hardware. If you have a big enough FPGA and enough time. Quite power hungry and quite hard work. You have to be quite knowledgeable. Another way is to use small scale components. Get some small chips with 4 gates on each or something like that, and put them together into a fairly largish machine. Need a lot of power, a lot of cooling, but it's good fun on a small scale. The last part I'm going to talk about is emulation. Emulation is where you use software to emulate the original hardware. That's what Turing said you could do. Any machine can, in theory, emulate another machine, and optionally you can add some nice hardware to mimic the original experience, so you have nice flashing lights and switches and anything else that you might want to do. So there are a load of things you can do. So I'm going to be doing some examples here of ways in which you can do this examination of old machines, and I'm going to focus mainly on a specific range of machines, and this is the PDP-8 range. The PDP-8 came from the Digital Equipment Corporation, which I mentioned before, and they were based in Maynard, Massachusetts. They got there about 1958. They took over an old mill, and they used that mill building pretty well until they went bust. I think it's now a shopping centre. But they made one machine called the PDP-8, which is particularly interesting. I'm also going to briefly mention another later machine for digital. They made many, and that's the PDP-11, which was a very successful machine. I'll also touch on other systems as we go through. Now, I should first of all mention here Oscar Vermeulen, and I hope I pronounced that near enough right. Thanks to him for a lot of the material in this presentation. He produced this machine called the PyDP-8, of which more later, and he gave a presentation on it which I couldn't go to. He gave me a copy of his slides and very kindly said that I could use whatever I wanted in my own presentation. So here they are. You'll see them. You'll see my style change. This slide that you're seeing now with the blue top is one of my slides. Oscar's have a different format. I have occasionally reformatted them, but mostly they're mine. So what was the Digital Equipment Corporation? Well, they started off in 1958 making laboratory modules, which provided just basic logic functions, and you can see some examples on the right. And they weren't into making computers, partly because the people who were funding them didn't think there was any future in going head-to-head with people like IBM and so on. And so they just made modules. But by 1964, they had persuaded their backers, in fact it only took a couple of years, that they could actually go into competition. And by 1964, they were producing these things called flip chips, which were modules again, hundreds of different types. And you can see that's one of the early ones on the right in the second picture down. It's got resistors, it's got real transistors, and no doubt one or two diodes and capacitors on there. So absolute discrete components at that point. And they were wired together into something they called a programmed data processor. They didn't call it a computer because their backers thought that they thought the backers would think that calling it a computer would be a bad idea because they'd refused to fund anything that was going up against the big computer companies. So it's something different. It's a programmed data processor. And they tried also to make their market one, which was mainly labs and things like that. And you'll see on the right there, that's actually a PDP-8, and we'll see more of that later on. Now, DEC were a very interesting company. Everyone calls them DEC and not Digital Equipment Corporation, or Digital Equipment Company in the UK. Very open culture. It was an engineering culture. They were very much about letting everybody know anything they wanted. So there's a book for everything. You used to be able to get books just by sending off for them. I sent off for many. I have a big stock of books from DEC. Some are about the hardware, some are about the software, some are about the programming. There are also books now, of course, written by ex-DEC people about the history of DEC. They're very interesting. But there's a book for everything inside here, and it's quite nice because you can find out pretty well everything you want to know. You could even get the circuit diagrams and so on, and they're available now too. But by 1987, they'd grown to 140,000 employees, so that was in what, 29 years. But by 1998, they'd gone. And the reason was that their flagship computers, which were things like VAXes and so on, were computers which were being outdated by the PC and by PC servers and so on. And they didn't really keep up with that. They did rather belatedly produce some PCs, but they were far too late, and they were expensive. In fact, most of DEC stuff was expensive. Very well engineered, but expensive. But they started off in 1959 with their first computer, which was, of course, the programmed data processor #1. And it was based on a computer from MIT called the TX-0, and I think they only made 2 of those or something. But it worked. By 1965, the 28th of April to be precise, they released the PDP-8. They had produced others in between. And this was a 12-bit computer. It didn't have bytes, it had words, and words were 12 bits wide. It's used as a lab computer quite often, or just as a microcontroller. We would use a tiny chip to do this kind of work these days. And in fact, you can make a tiny chip emulate a PDP-8. The PDP-10 family was their sort of mainframe end. Came out at much the same time, and it was actually based on the PDP-6, and it was a 36-bit machine. That might seem a bit odd, but quite a lot of the early machines were 18 bits, and they just doubled this up. And it was pretty well a mainframe. But they kept the whole mentality of the mini computer with it, as you'll see on the control panel later on. The PDP-11 was the most successful one. 1970 that came out. University of Kent got their first one around 1973, I think, and I played with it. A 16-bit mini computer, very successful. They made a lot of those, and they didn't stop making them until the early 1990s. And they were a really, really nice machine. I have 4 of them. And then they went on to bigger things. The VAX was a 32-bit computer, which was a lot more powerful than the PDP-10, and it was their next generation thing. It was based on the PDP-11, and the architecture is very similar to a PDP-11. It's just bigger, 32-bit machine. And the VAX was around until reasonably recently, certainly into the millennium, and then it was replaced by other things. So let's start with part 1, which is relatively short. This is what I call machination, for the want of a word. And this is about the real machine. If you're a sad, rabid enthusiast like me, then you will have a real computer from back in the day. Usually it's quite a small one. I have PDP-11s, I have some VAXs, small VAXs, but that's all. Anything else is beyond the power resources in my house, it's beyond the tolerance of my wife, and it's beyond the space as well, and my wallet. So there are things you can do. It's hard to come by, this hardware. You can trawl around for parts of it on eBay, but usually you're finding somebody who's splitting a machine and they're selling bits of it at inflated prices. But if you've got about a small PDP-11 with 2 disks, which I have, that consumes about 1.5 kilowatts. So we're talking about, anything between 20-25 pence an hour to run, which over a time is quite a lot, and a lot of noise too. The PDP-10 would require me to get the house wired for 3-phase, which would be quite expensive. But let's look at where the story starts. The real PDP-8. I'm going to concentrate on the PDP-8, as I said. This machine was the single most popular 1960s and 70s mini computer, and it came in a variety of flavours over time. What you're seeing on the right is a PDP-8i. There were various other ones, but that's the I. That's not the earliest one, which was 65. The I came out at around 68. And that's a minimal one. It hasn't got much in the way of disk or tape or anything else. It's just probably got a teletype and a paper tape reader and punch on the teletype. And it has lots of these nice switches along the front, which is typical of nearly all of the DEC machines, except for the VAX. But even that had some inside. This is actually the birthplace of many important software concepts. You see an awful lot of what went into the PDP-8. You'll see again later on, including its operating system. It's a sort of machine you would use in a laboratory. The first one I came across, I did physically see it once, was actually connected to a mass spectrometer in the chemistry department around 1972-73. And a guy who was a final year student, whose name I think was Paul Berry, if you're out there, Paul, let me know you've heard your name. Paul was actually compiling and then running programs in PDP-8 assembly language for his final year project. And he was able to cross-compile them from the mainframe, the ICL 4130 that we had. And so I used to see the listings, although I never went much into chemistry. Its unique evolution was, first of all, it started off with just paper tape and a teletype. And we'll see a teletype in a minute, but a teletype is basically a very slow typewriter, 10 characters per second, designed for communication over long distances for sending messages, really. And you could make it punch paper tape of what was coming out and then feed that back in. And we went from that, attached to early PDP-8s, right up to a comfortable desktop operating system that you could actually, you could sit the entire box, that bit with all the switches, on your desk. It would have everything inside it, and you could sit and use it in much the same way that you could use a PC, really, and it would have similar capabilities, to be honest. So here we have a PDP-8 picture. I'll just show you that first. The PDP-8 itself is set on that little pedestal on the right, and what you see on the left is a teletype with some extra bits added on the side, but the teletype is that part with the keyboard and everything else. That's a rather unusual model of one. But why would you want to play with a PDP-8 anyway? Well, if you want to know how computers work at the lowest level, you want to know about assembly language, this is probably a good place to start because it's a really simple assembly language. There isn't a lot to it, and yet you can do an awful lot of work with it. It shows you where we came from in terms of computer history. It's probably the first machine that was accessible as a single user machine without an expert. You would tend to buy this thing for your lab, and DEC would help you to learn how to use it yourself. You wouldn't employ an IT department or an IT guy to do it. You would do it yourself and sit down and use it in your lab. The programming had to be of necessity quite concise because obviously you were trying to fit it into quite a small machine, and we'll see how small soon. So you had to be pretty good at programming, and you learned how to save space, and you certainly didn't have what we would call today bloatware. There isn't room for it. And you got blinking lights, or blinking lights from the old joke. You have lots of lights. The PDP-8i, I think, had 89 lights on it, some of which were quite superfluous, really, but they're really, really good. So I think that's enough reason to want a PDP-8, and we'll move on and see how we get there. So I talked about blinking lights, and here we have a close-up of just part of the PDP-8's front panel. And you can see that you have things that tell you where the program counter is. That's the register that tells the machine where the next instruction is coming from. The address in memory it's accessing. The data in the memory buffer that it's getting in and out of memory. The accumulator where everything happens, what the current values are in there. These are ones and zeros on the lights. And then the MQ, the multiplier quotient, which is an extension to the accumulator for big numbers. Some of you may have heard of the fetch execute cycle. Well, you can find out whether it's fetching or executing by looking over on the right here. You can see the lights that show you which it's doing. If it's doing, it's got interrupts turned on, and then you can see that because they will be that light will be lit, and you've got various others to do with input and output. Most interestingly, in that little enclosed set on the left, on the right there, are the column of 8 lights labelled AND, TAD, ISZ, etc. The machine has 8 instructions, only 8 instructions. There's a 3-bit instruction field in the for opcodes, and that shows all 8 possible instructions, and it shows you which one it's doing most at the moment. Because the lights are obviously quite slow, what we're seeing here is that it's doing mostly jumps and input-output instructions, because those are the 2 that are lit. The others would glow depending on how often they were being used. There's not a great deal of point to all that, but DEC used to like to have all these wonderful lights. You can single step the thing. You can make it do one instruction and stop. The single step switch is the second from the right at the bottom there. And that's quite a nice thing to be able to do. You can see what your program's doing. These days we would use a debugger like GDB on Unix, for example, to do much the same thing. But here you did it with the actual hardware, with the actual iron, as it were. You can see the execute instructions. You could obviously see which one it's doing with those lights. You can also see the effect on the program counter, the memory address, the accumulator, and so on, and some other things that are off the picture. So you can see these registers. You can also set their values. It's possible to deposit values into the various parts of the machine by using the switches at the bottom. Some of them are spring-loaded and do special things like deposit into memory. So you can set up a value on the switches and then put it into a place in memory. PDP-8 is really similar to the modern microcontrollers, things like the Atmels that you get on an Arduino or something like that. It's very close to the hardware. It rewards very efficient coding. As I said, you have to not have bloatware. But here you get to see what you're doing because you've got the switches, you've got the lights and everything else. So having a PDP-8 would be really nice, I think. Much more fun than this rather anonymous small black chip. So where do we go from here? Well, you can program it, of course. You can program on the PDP-8 the software available. It's got assembly language, it's got BASIC, it's got Fortran, if everyone remembers that, formula translation, Focal, which is their own language, Algol, which was a language of the 60s, Lisp, a Lisp processing language, Forth, which is a language you occasionally see around, a stack-based language, and all of these things are things you can play with. I'm not quite sure where the cat comes in, but I always like to have cats on pictures, so I don't see why not. What you see on the right there is a PDP-8i again, and above it has got something in green livery. That's what the deck used for the PDP-12, which was a version of the PDP-8 which had a sort of leaning towards just lab work, and that's obviously some kind of lab interface. And the monitor on the right, the screen there, is actually a graphics terminal, or graphics screen, and you can see it's drawing something on it. The operating system is called OS 8, and there was a later OS 8 which came out from Apple, I think, but this is the OS 8 from DEC, and it came out in the late 60s, and it was a cut-down version of what they were using on the PDP-10. It's an amazingly sophisticated operating system for its size and for the machine it ran on. It's an ancestor of CPM, if you've come across that, control program for microcomputers, and of MS-DOS, which pretty well mimicked CPM. Its command structure is recognizable to anybody who's ever used DOS. They also had something called TSS-8, Time Sharing System 8. This was a multi-user system for the PDP-8. It had 32k words of memory. Yes, just 32k. And it could run up to 8 users running remotely, all doing their own thing, in what was essentially a virtual PDP-8. Quite amazing, really. I'm not sure it was used very much in practice, and part of it was a sort of just a bit of trolling at IBM, because the IBM 360, their mainframe, had something called TSS 360, and I guess somebody just thought it would be a joke to call theirs TSS 8 and to do, well, quite a lot with it, and a lot more friendly than TSS 360 as well. And it probably had the earliest chess game, which was Checkmo. The Checkmo is still available if you have a PDP-8 or an emulator to run it on, so you can go and play chess. And the earliest adventure game, Advent. Advent may be known to some of you better as Colossal Cave. Colossal Cave has been around on practically every system now. It was written in Fortran at one point, it's been written in other languages. I first played it in, 1973, I think, late 73, and I got quite obsessed with it, and I ended up carrying around a big map on several sellotape together pieces of paper of what the Colossal Cave was like. But that was only one version. It did evolve over time. So, quite a nice thing, actually. Oh, and there we see one other game, Space War. Space War is still available if you have a compatible graphics terminal, and you can see it's quite weird. You can just about see the spaceships there and so on. You can play Space War if you have the right things. Even the emulator will run Space War as long as you've got a suitable screen. So, what's the historical significance of the PDP-8? Well, I guess it's the machine that made, as it says there, the jump from paper-shaped dinosaur to personal computer. It started off as a machine like the very first one we saw, the floor-standing one, which was just a box really with a power supply in the bottom and a teletype and paper tape on that. And then it moved on to being something with discs, something with a multiple terminals perhaps, with tapes, and later on in life it became a desktop machine, and in fact they had one version of it called the DeskMate, which was simply a PDP-8 turned into a word processor. We're talking early 1980s here, a single chip machine by that time. So it's quite significant, and it spans all of that. But it was actually one of the first ones to move to being something like a personal computer. And it's a sort of in-between machine. It came along after the evolutionary direction was fairly clear that we were going to go to a sort of von Neumann type machine that would be available in departments, but probably not to everyone individually. But certainly before the architectures got settled, the architecture of the PDP-8 turns out to have been a bit of a dead end because people went for byte-oriented machines in the end. It was the first mass market computer. They sold many thousands of these, and programmers got quite a wide audience for what they were doing with them. And DEC, as I said before, had this open source mindset, although it wasn't called that then. They had the engineering attitude that you could know anything you wanted to know about the machine. You could take it apart, you could look at it, you could fiddle with it, and they would help you as much as they could. They might charge you for it eventually, but they were very, very helpful people. And it gave many of the early pioneers their first exposure to computing, and that shaped them for better or worse. I think for better in many cases, because they had the idea that you had to fit things into a small space, and you had to be economical. There might have been other things as well, of course. So, paper tape dinosaur, let's look at that a bit more. We've got pictures here. First of all, this is what you had to do in the early days. You would have to load a tape. By tape here, I mean a punched paper tape, about 1 inch wide with 8 holes across it, corresponding to what we would now call a byte. And you would load the editor tape into the computer, and that would mean loading a program, which was your editing program for preparing your source code. So you would actually have to put that into the paper tape reader and wait for it to load. And if you only had a teletype, it would load at 10 characters per second, so you would be pretty careful to get this right. You type in your source code, and then you would punch that out on the paper tape punch, which again was 10 characters per second. So you now have your source code on a roll of paper tape, and yes, you had to wind it up. Although DEC did find some ways around that. Then you would load a tape with the assembler program, and that would get loaded into the memory of the computer. And you'd follow that, although it doesn't say that here, by a copy of your source code, of course. So your tape for your source code would go into the computer. That would then, if it assembled correctly, you could then punch out a tape of a binary tape of your actual program ready for running. And then you could load that tape back into the computer and run your program, and then start detecting your bug. And if it did have a bug, which of course it would have, then you go back to the beginning, as the arrow shows. So it's quite a tedious and time-consuming process, and you were probably, in the hour you were probably allowed on the computer, you'd probably get 2 goes, something like that. I know this from other computers. By 1968, you could just load the tape of the Focal system. Focal was a language that DEC developed, and it was a bit like BASIC, I suppose, in it was interactive. You could just sit there and use Focal. You could type in your code, and you could run it, you could change it, you could run it again, you could change it, you could run it again. So that was a lot better. That was definitely an evolution. And you cannot imagine what the early stuff was like unless you suffered on it. And I did actually, in about 1972, we were using a fairly small 16-bit computer that only had minimal disk facilities. And so we were doing it like this. So we evolved, and we evolved in a good way. They produced something called DEC tape. These are 2 DEC tape reels. Left-hand one's the full one, and the other one's a take-up spool. And this is drive number 1, as you can see. And although you can't really see it too well, just above the 2 reels are 2 sort of quarter circular pieces with that white thing pointing up at the top. The white thing is the read-write head, and the other 2 things are guides to take the tape up from the tape on the left, to the reel on the left, over the read head and down to the right. Read and write. The tape was quite wide, and everything was recorded twice on it for redundancy. That would have been okay, but actually the outermost tracks were the clock tracks, which actually were essential for reading anything on the tape. And the outermost tracks used to scrape against the edges of the head and get damaged first. So that was a bit of a design boo-boo. What you can see above on the right is the drive number, which was drive 1, numbering from 0, of course. And just to the left of that number, you'll see 2 switches, and they were for things like rewinding and for write protecting the tape. So you could flip that switch and make sure that your system tape, for example, wasn't overwritten. What was interesting about DEC tapes, they weren't like normal tapes, they were formatted. and they had sectors on them, if you like. They were called blocks, and so they worked like a floppy disk. And you could, unlike most tapes, you could go to any given block on it and just overwrite that one block with the new contents. So it worked just like a floppy sector would. Low tech, but it worked. I think they held about 350k bytes in modern terms. And that meant that you had something which was updatable, easy to use, and was much cheaper than a disk. Disks were still way out of range financially. These things could be carried around in a largish jacket pocket. They're only about 4 inches across, something like that, and they worked very well. And you put your operating system on that, and even a swap area, believe it or not. Then we have the terminal, the teletype being replaced by something rather better, a screen. Even if it was only a glass teletype, as they were called, that just scrolled up. And that gave you interactive computing in a much better way. We started off using a editor called Tico. If you want to know more about Tico, look at Wikipedia, but it's an editor which frankly had a rather strange user interface. In Tico, every key on the keyboard, including all the control characters, is a command, and a set of Tico commands looks rather like line noise. But they moved on to something called WPS8, the word processor, at the end of the era, which was a desktop PDP-8 built into something like that, and it would provide you with a word processor. So it evolved a long way over time. And you can see where this was going. It was taking us towards the personal computer. And yes, there have been other attempts at personal computers too, from various 8-bit machines based on the 8080 and then the Z80. But the astonishing feats here, I did say a bit about this earlier on. TSS-8, multi-user operating system. It was devised by a student actually, and I was wrong about 8 users. It's 17 users using smoothly running virtual machines. 32k computer, 32k. That's 12-bit words, so we would call it 48k bytes, I suppose, roughly. It doesn't even got a stack pointer, this machine. The architecture is incredibly basic. It has one accumulator, one carry bit, or a link as they call it, and very little else. And the name, as I said, was intended to troll IBM. They built PDP-8s from 1965 all the way up to 1990. And they started off using diode transistor logic in the very early days, actually discrete stuff in the very early one. And then they worked up to using the 7.4 series logic in about 1970 and onwards. 7.4 series was quite power hungry and not very fast. And they moved on to a single chip microprocessor. Harris, and also there was second source by Intersil, the Harris 6100. And then later the 6120, which is an enhanced version, in a single chip. And I actually have a machine that I built which has got an HD 6120 in it. It's not ideal because the HD 6120 has these enhancements which make it incompatible with TSS-8. So you can't run TSS-8 on it, which is quite annoying, but still. But they're all the same PDP-8, same instructions pretty well, apart from that bit. So 50 years, nearly, of active service. And that is quite amazing. They're still around. In 2016, apparently, this is going to Oscar, a 1970s PDP-8 still ran a CNC machine. Somebody is still making money servicing PDP-8s in Germany. If it works, you leave it alone. Why not? So yes, some astonishing feats there. So that's machination. That's the real machines. Now let's move on to the practicalities. We can't afford these machines. We can't find these machines. So what do? Well, we can replicate them. We can build a replica in hardware. And obviously, if you can get the original components, that's easy. You can still get the HD 6120 if you try hard enough. And the chips to support this are also quite difficult to find. You need some basic RAM chips, static RAM I think it is. You need a serial port and a UART chip. and you'll need some sort of disk controller, although the disk controller can be done with more modern chips. And of course you can use things like gate array logic and so on to build you whatever logic you need. Another way you can do it is to build the whole thing from individual components. People don't tend to do that, but people have done it. There is a book which actually was intended for a university course, and that book contains all the details apparently on building a PDP-8. And then you can use a field programmable gate array, which I mentioned earlier, which is logic building blocks on a chip, and you program it. You need to build up a lot of expertise for that, and you'll need quite a big one, and you'll also need quite a lot of power. But it can be done. You can build things from components. Now here's a real PDP-8E, which is one of the earlier machines. It's the ones that probably you were talking 1965, 66, something like that. And you can see it's got some nice stuff on it. You can't see really on there, but in those rectangles surrounded by the coloured stuff in the top middle are actually a set of lights, and they can be lit up to show memory address and what have you. The switches can set things which you can then put into memory. It's quite common to want to lock these things, so the power switch is a lock, as you can see on the left. So that's a real one. The replica in this case is a thing called an SBC6120, single board computer, and it's using the HD6120. So before we go on to that, let's look at the PDP-8E in a bit more detail. You can see the lights on there, and there's a video here as well.
So you set the address you want it to start at, which in this case is 0040 in octal. So you load that address, and then you look up the magic code, which the first instruction is 7001, and you deposit that in the address. And I've turned the switch so you can see the data content, so that's 7001, and then 2051, and then 5041, and 5040. So now the program's in there. Set the address back on the switches, which is 0040, load that again, clear the accumulator, let it not be halted, and make it run. And, oh, I've obviously done that wrong somewhere.
It's alright, we can do it again.
Never mind. Let's see, 40, press load, let's see what's in there. So that's 7001, 2051, 5041, 5040. That should work. Press load, clear. Continue. It's not happy. I think this machine actually has a fault, and when it gets hot, which it will be now, it's just decided not to play. But that's the sequence they got used to put it in.
Right.
Very simple.
Cool. Yeah.
As you can see, he was talking about putting things in octal. Octal base 8 arithmetic. It's convenient because you can get 3 bits can be expressed in octal, and so you tend to work in octal. Most of the numbers that you used on the PDP-8 and on the PDP-11 were in octal. In fact, on most machines that DEC did, the exception being the VAX. And there they moved to hexadecimal, which is 4 bits, it's base 16. Okay, so let's go on to the SBC6120. This is mine. I built this on a single board, as you can see, and I made this one in a small box so I could carry it around with me if I needed to. It's very basic, and it's quite a nice little machine, I think. It works well, and the only connections it's got are a power, which is top right, a serial port, nearly top right, the power, the round thing, the serial port right in the corner at the back there, a reset button on the front, which is not really very visible, and some status LEDs, which are just to the right of the white screw at the bottom left of the board, a little block of 4 LEDs. Reset buttons in between the two. What's over on the right is CF card, compact flash card, being the disk, and a little power control board over there just to allow me to do various things. So it's quite a nice thing, and I think we've got some yeah. The compact flash card actually acts as storage for multiple 2 megabyte hard disks. The PDP-8 didn't have a hard disk any bigger than 2 megabytes, couldn't really handle that, so that's all you have. But hey, it works. This is a deluxe version, which is I built later on. It's got the same sort of board in it. I've got a second board, but I built this one onto a panel with pretty lights. I'm not very good at woodwork, but here it is sitting there. And you can see it looks remarkably like the PDP-8E. The main difference is that the switches are all one colour. Nobody's come up with some nicely coloured switches yet. People have attempted to colour those switches, but it doesn't quite work. The sort of shades of brown, if you like, and orange that the PDP-8 has are characteristic of that particular line of machines. The PDP-11s used shades of red, and some of the other machines use shades of blue. The link machines, the laboratory machines, the PDP-12 type things, use that rather sickly shade of green that you saw on the lab peripheral earlier. So this is mine. All it requires is power and a serial port again, which are on the side, and it will quite happily run programs. Serial port can be connected to either a real terminal or to an emulation thing on a PC, which is what I do. And what's interesting about the SBC 6120 is it's got a sort of ROM BIOS in it. It's got a it doesn't actually, the real machine doesn't have a ROM, of course, but the 6120 SBC 6120 does, and the ROM's got some file transfer capabilities in it. It's also got some debugging stuff. You can single step and so on without going to the switches, and it's an easy way of booting off the disk rather than having to key in a bootstrap. But that's about all really. I did modify the ROM in mine slightly because it wasn't quite what I wanted. But the point is, it's running real code on real hardware. You have it's a replica. It's a working replica. So it's as near to the real machine as you can get these days. And it can use OS8, and it can compile and run programs in various languages. As I said, unfortunately, it won't run TSS8 because of the enhancements to the later versions of the chip. That's a bit of a shame. But apart from that, it's a PDP-8E essentially, and so it can do what a PDP-8E does, which is very nice. So if you want to have something to stick on the wall or something, yeah, it could actually be made a lot flatter than that. Then it will work quite well. Now, we were talking about building things out of real components, and there is this guy who's done that. He's actually built an entire discrete computer in his house. He used it to play Tetris. It's ridiculously large, as you can see, but it's quite educational, I suppose. And if you look up mega processor on Google, you can find more about it. That's a picture of it in the room with a sort of three sides of a room. It's quite silly, and indeed there's a link for you. But that is even madder and even sadder than me. So there we are. Another one is the Monster 6502. 6502 was a microprocessor, 8-bit microprocessor, which the BBC microcomputer used. If anybody has ever come across the BBC microcomputer with the one with the row of orange keys at the back, then that is that had this CPU in it, and somebody's built one of these in discrete components and put it into a box and made it look quite nice. So you can have a look at that as well if you like. So that's another way of doing a working replica. Now we move on to emulation, and this is probably the most accessible thing. The other things all require you to pay possibly quite a lot of money to get something working. The emulation will cost you nothing if you have a PC, or even, heaven forbid, a Mac. Then you can do it. What you do here is you use this newer machine of yours to pretend to be the target machine, and you can emulate whatever computer you want. Now, to give you an example of how practical this is, you might think, well, that's going to be really slow because the emulating the machine in software is going to be much slower than the real thing. Remember, these weren't fast machines. And if you look at the University of Kent's VAX cluster around 1991, we had a pair of VAXes running not very efficiently in dual processor mode. If you were to just take a single one of those CPUs, it would do a speed of about 8 VUPs, VUP being a VAX unit processor. It's based on how powerful it was compared to the first VAX that was ever produced, which was a 780. So 8 VUPs was quite big. It's about 8 million instructions per second. So that machine did 8 VUPs. Now, if I run on my 3.4 gig typical Intel PC, if I run the VAX emulator on that, I don't get 8 VUPs. I get about 10.5. That shows how much CPU technology has come on. So emulation is practical in terms of speed. And all it does is emulate it by fetching an instruction from an emulated memory, which is just an array with all the instructions in it. So you have, if you're emulating a 1 gigabyte machine, then you have a 1 gigabyte array with the machine instructions and data in it. And you fetch those instructions out of that array. You see what they're meant to do. You do it in code, and then you update the memory as appropriate. You emulate peripherals in a variety of ways. A disk tends to be just a fixed file, so you have an array of blocks in a file, which is basically all a disk is. A tape is a file as well, but it has structure in it. It has headers and trailers on areas of the file which effectively tell you what block number they are, how long the block is on a tape, because you can write variable length blocks. On a tape you have something called a tape mark, which is effectively a 0 length block that allows you to indicate the end of a file, and so you have to have some sort of indication in the structured file for that. But otherwise tapes are pretty simple. I mean, the structure is really easy. Punch cards, punch paper tape, they just become files with data in as they appear on the media. And terminals are usually virtualized onto an SSH or telnet connection. So you just tell the emulator to listen on a certain port, and you telnet to that port, and you've got a connection to that serial port. So it's quite easy to emulate those things. There's a lot of emulation software available for a lot of targets. You can do pretty well most DEC machines, all from the same author. Bob Supnick, who used to work for DEC, has done a superb set of emulators called SimH, Simulator for Hobbyists. There's also IBM mainframes. There's a wonderful one called Hercules, which does the IBM mainframe 360, 370 and onward series. Some other IBM machines are the older ones. You can emulate the PC, and that can be useful if you're trying to run some old software that won't run on a new one. But there's a lot more than that. There are HP machines, there's Data General machines, all sorts of machines you can do. So emulation does work reasonably well. So let's look at SimH, because SimH is Bob Supnick's thing. It's really nice. It's what got me started. And for DEC machines, you would probably use SimH because it's nice and consistent across all the various DEC machines. It's written in C. It's very portable. You can find it on pretty well anything you like. I did the port for FreeBSD. It's available on Linux. It's available on Windows. That covers most of the modern stuff anyway. And what it consists of is a framework for an emulator. So all the stuff you need to emulate tapes at the detailed level of the structure of the file, for example. And it gives you terminal access via telnet, and it gives you a basic disk framework, and then you then build your emulator program for a particular machine on top of that, using all the same facilities. So you don't have to start from scratch, which is quite hard. Very well designed. Oh, there's an example of a few machines. The Altair, the Honeywell 316 and 516, which I'm very keen on because I used to use a 516. In fact, for my final year project, I modified the CPU of a 516. HP machines, a 2100 and now the 3000 as well. They're currently unavailable, about to become re-available because somebody's re-engineered them. Lots of old IBM machines there, you see. Interdata, they once had Unix on. Data General Nova and Eclipse. If anyone's ever read The Soul of a New Machine by Tracy Kidder, which is a really interesting book, that's about the development of the Eclipse. And the DEC PDP, all lots of numbers as you can see, and the DEC VAX, which was their last big machine really. So Bob Supniks wrote this. He was a CPU expert for DEC and knew a lot about the detailed inner workings of the chips. And then other emulators have been added by various people to that framework. I'm working on one myself. And if you want to run SimH, all you really need is a Raspberry Pi. But you could use an Arduino or an ESP32 if you tried hard enough. Well, that's not normally the case. But the easy way to start is on a PC because you've got everything there. But if you wanted then to run SimH in a sort of an isolated way, then get a Raspberry Pi. Raspberry Pis are cheap. Now what this is about now is actually Oscar's emulator for the PDP-8, and he calls it the PiDP-8 because what sits behind there is nothing more really than a Raspberry Pi. You can see that the panel looks remarkably like the one that was used by DEC. It's actually a 2/3 size replica. It looks pretty well the same. You'll notice that even on the right, those lights and so on are the same. That's a block of lights, and one for each instruction. The switches are the same. Pretty well everything's the same apart from not having a key power switch. It's even got the bootstrap, the RIM loader as it's called, read-in mode loader, printed on the panel just as it is in the real one. So that's a rather nice thing. And Oscar designed this. He designed the panel and the case and everything else and how to use it and the circuit board and modified SimH to interface with the lights and everything else, and it works really well, and I have built one of these. So it's a replica of the 1968 PDP-8i, and you can use a Pi 0 if you like, but if you use a Pi 2 and above, you can even access it via Wi-Fi, which is what I've done with mine. I think I've got a Pi 3 in mine. And the only connection on the box at the moment is a socket for putting some power in. Everything else you get in via SSH over Wi-Fi. So that's rather nice. Your terminal could be anywhere. It's open source hardware. You can get the details of the board and how to, the necessary files you can send off to a PCB fabricator, and nothing else is needed. But you can buy a kit from Oscar, which I would thoroughly recommend. It's a very nicely put together kit, and you can build it yourself. So this is Oscar's stuff, and what he's saying is, what were his design goals for the PiDP-8? Well, the idea was that you could really experience and live through the various phases in PDP-8 evolution. So to do that, he provides you with all the various parts you might need, and obviously you've got the panel. So by using the panel, you can do pretty well anything you could do on the original PDP-8. But what's important is that these switches here are specially arranged so that when you power the thing up, it does something special. It starts it off, if they're set to a 1, then it gives you a naked paper tape and teletype PiDP-8, and you can emulate the paper tape with files. You can run it OS8 off a DEC tape, should you want to. You can run OS8 off a hard disk. By setting it to 4, you can run TSS8. Set to 5, you can run Space War, which is a video game, and you need the right sort of graphics terminal for that, or an emulator on a PC. Or you can run ETOPS, which is another multi-user OS8. So you can actually experiment with all these different levels of what the PDP-8 did over its life. Quite apart from that, you will need to have things like your tapes, particularly for the first one, for the naked paper tape. And the way you do that is you stick them onto USB sticks, and you can do little proper original DEC labels for them if you want. And the idea is that when you put these into the USB port, you obviously have to cut a hole in the case for that, they become paper tape and it will read them in. So you can really get an idea of what it was like, except that your paper tapes will read a damn sight faster than the paper tapes did back in the day. But the idea is you can see what you had to do and the steps you had to go through to build a program. So that's certainly design goal number 1. But the other design goals were, first of all, secondly, it should be pretty. So you have an existence in the living room for some value of living room and tolerant Wi-Fi, I guess. It's something that is nice to have on the shelf somewhere. Anyway, it's in my workshop and it looks good in there. It's got to be practical. You need a real terminal for it, or a teletype, or just use Wi-Fi, but you're going to be able to use the thing easily. And it's going to be somewhat useful. Because it's running on what is essentially a multitasking operating system, what's running inside the Raspberry Pi is actually a variant of Linux, or in my case it's going to be FreeBSD, but because that's running in there, it will run a PDP-8 with up to 6 users, which I think is the limit on terminals, and you can still use the Raspberry Pi. So you plug in a console and you can use the Raspberry Pi as a normal Linux machine as well. So it's somewhat useful in other ways as well. So you've got a Linux box in a very small space. And you could even use it as a decorative Wi-Fi router. But that's probably too sad even for me. Okay, let's look at the hardware. The design goal here was to try and minimise the hardware and keep it simple and cheap. And there isn't actually very much to it. What you have here is a single board, as you can see, but there's a little subsidiary board just to help hold the switches up, but it's really not a circuit board as such. And that board has mounted on it all these 89 LEDs. It has one chip, which is needed to drive the LEDs, and pretty well nothing else, apart from a few diodes and resistors. And the Raspberry Pi just mounts onto a socket, as you can see. And the top one is the back of the board where the Raspberry Pi is. The bottom is the front of the board where the LEDs and the switches are. And all you have to do to build it is really solder on the resistors and the chip and the 89 LEDs, which is a bit tedious, and then just fit the Raspberry Pi on. And it's ready to go. So you need a Raspberry Pi. There it is. There are the 89 LEDs, 26 switches, because that's what the machine had, 26 diodes, 15 resistors, and there's a chip which is optional, but it helps to make the LEDs a bit brighter. That's it. So quite a nice, simple layout and simple design. Not a lot to go wrong, really. The most difficult part of building it is actually soldering the switches on and keeping them straight, and having enough heating in your soldering iron to do it. Software, well, it starts off with SimH, but SimH has to be modified, of course. It's probably the best PDP emulator there is, and it doesn't cost anything, and it's just simple to use on a Pi. And the emulated PDP-8 is connected to the front panel hardware. The GPIO pins on the general purpose input-output pins on the Raspberry Pi can be used to send signals to turn on the right LEDs at the right times and to read the switches. So that's what happens there. The CPU exports its register values and sends those back. It does that 60 times a second to the front panel. So you can argue the front panel is never always quite up to date, but it's only a 60th of a second off. And that's the best you can do with emulation, really. Access to the terminal, as I said, is via a hardwired connection. You can actually plug in a serial port if you want to the Raspberry Pi, or you can hardwire the network in with an Ethernet socket or using Wi-Fi. So lots of options there. This is how the LEDs are driven. This is rather interesting. It's actually quite hard to drive that number of LEDs individually when you've only got a few, I forgot how many there are now, but there's about 20, I think, something like that, GPIO pins on the Raspberry Pi. So this is an idea that was nicked from something called the Kim 1, which was a computer back in 1976, and it works pretty well. So what you have is an input-output pin coming out of the Raspberry Pi, which is set to high, 3.3 volts, and that drives one side of the LED, and the other side is another pin which is set low to actually take power. It syncs it. If you set the I/O pin, the one on the ones at the bottom to high, then there'll be no voltage across the LEDs and they won't light. So that allows you to handle one column, one row rather, with a whole set of, well, how many it is, 6, 9, 12, 12 of course, pins there, and one pin at the top. And then what you do is you have other pins which are set so that they also drive a row, and the columns are run from the same set of pins as before. But because the one on the left is set to no current, to low for no current, you don't get any LEDs lit. So you could light a selection of one row just by using these pins, which is only 16 pins. By setting a different pin to high on those 4 on the left, you can select a different row. By changing the values on the bottom, you can select a different column. And you can see how it works all the way down. What you can also do is what's called tri-state the I/O pins. This means that they're neither high nor low, they just don't do anything. And by doing that, you're effectively taking the LEDs out of circuit. And what you can then do is set another pin on a separate row to low, which becomes a current drain, and then you can actually feed power through switches, and you can detect which of the switches are set by seeing which ones have current flowing. That allows you to find out what the switches are doing. So we can drive all these LEDs, and we can also sense the switch values pretty easily. That's an idea of how it works. There's the other example there of doing the switches. So this is all made as a kit. It's educational, it reduces the cost. I think Oscar wants to build them all anyway. But you can see on the right there, you have at the bottom the flat acrylic panel, nicely screen printed for you. You have the circuit board, blank circuit board ready to go. You have the little board which just is there to support the switches, and then you have the other various components working your way up. What you have is a set of resistors, capacitors, diodes, LEDs and so on, various bits and pieces. The switches, there are 4 different types of switches. There's white ones and brown ones, and for each of those, some of them are click on and off, and the others are biased, so they just press and let go. You've got the chip at the top for driving the LEDs on the left. You've got the socket for plugging the Raspberry Pi into, that long black thing, and a couple of blocks of wood, one on top and one underneath the other 2. Those blocks of wood are actually used for mounting it in the case. The case is right at the top, and it's actually a kitchen storage box from Amazon, costs about £8. I've got a spare one now because I'm going to try cutting different holes in it. A kit means you haven't got to think about much. Your design options are there. You know, they're all done for you really. The only thing you've got to decide is how many holes to cut in the case and what to make accessible. The parts are all through-hole non-SMD components. They're easy to solder. It's mechanically very simple. There's no real precision work. As I said, possibly the most difficult thing is getting the heat in from your soldering iron for the large lumps of metal on the switches. And what he really thought about was, how can you work out what problems there are? You know, if you've got a single symptom and a single cause, that makes it nice and simple to put right. And the repairability of mistakes. The most expensive part in the whole thing are the switches. Get that wrong and that costs you money for replacements. But it's a nice kit, and it doesn't take all that long to build. I took my time, and it probably took me about 4 or 5 hours. But there are other projects in replicas apart from the PyDP-8. Oscar has done the PyDP-1170. Much the same kind of thing, as you can see. Uses very similar circuitry, although it's simpler because there are fewer lights. There are more switches, of course, because it's a 16-bit machine. But it has a custom-built case. This is a rather nice plastic moulding, which actually looks like the original. So do the switches look like the original. It's 2/3 size again. What you're seeing at the bottom is a real PDP-1170. What you're seeing at the top is the PyDP-1170. And it's in a case which is essentially looks just like the front panel of the original. which doesn't stand up too well, so it comes with a shaped piece of wood to sit it on. That's all part of the kit, and it works really nicely. So there we are. And you can even fit a switch on it if you want, a power switch. But there are other projects, the Kim Uno, which I haven't seen myself, a CP Mega 88, and you can go back further. There's an Altair Arduino, you can imagine what that is. It's an Altair machine but built around an Arduino, and the little GP30. So all sorts of different ones. But I think Oscar's are really nice. Oscar is looking at doing, and I think it seems to be well on the way, doing a PyDP-10. Now the PyDP-10 is going to be interesting because DEC had this mini computer mentality, and the mentality was that everything should have lots of lights and switches, certainly in the early days. And the PDP-10 was a 36-bit machine, so yes, you get 36 switches, you get rows of 36 lights, and that is going to be even more of a challenge in terms of driving all those LEDs and reading the switches. And he's worked out a way of doing that, he tells me. So that's very interesting, I think, and I can't wait to get my hands on one. I've programmed a PDP-10 and they're great fun. And they're a proper multi-user machine. And usable for real work. If you want to play with virtual replicas, some of which are online, go to retrocmp.org, have a look there. And hopefully we'll do more important machines like this. I'm looking at doing a Honeywell 516 at the moment. The 516 emulator exists in SimH. I have the details of what the panel looks like and measurements. So I got those from the Science Museum. They very kindly let me go and measure one. So I'm hoping to get that done probably quite soon. There are many other emulators just inside SimH. Obviously the 516 one there, there's a VAX one. The VAX doesn't have any interesting front lights, unfortunately. You can't do a lot with it. So it's not a real much of an experience building one of those hardware-wise. But just the emulator itself is good fun. You can sit there and run a VAX, run VAX VMS or Berkeley BSD or something like that. If you look on my website, you'll find there is actually details of how to run the last version of BSD for the VAX on your PC. But it would be nice to build panels for more of the Simnic emulators, and I'm certainly going to have a go at the Honeywell one. So the PDP-10 is going to be a challenge, but since I wrote this originally, he has actually got as far as doing this, and you can see what I mean about all the switches and lights. There's a lot there. The later PDP-10s didn't have that. This is a KA-10, which is a relatively crude version of the PDP-10. Its memory management consisted of just two separate areas on the of memory. You have what we call a low segment and a high segment. The low segment was writable, the high segment wasn't, and your program would go into the high segment and could be shared with other machines. So that's something which I think he's going to be doing a KA-10 panel because that's the one that looks good. So there we are. I mentioned the Honeywell one. Oh, well, there's a picture of it. I've forgotten I got that, but that is actually a picture of the one in the Science Museum. 16 buttons which light up when you press them. They're the equivalent to the flip switches, and you can clear them all in one go by pushing the clear button on the right hand end. Various other switches for setting modes of what you're looking at, and single stepping and the like. Some of those switches are spring loaded, and there's the go button on the right, which is a nice big green one, and when you press it, it lights up green. It's really good. I've actually used one of those, and in fact I've used that very panel. That is the one that's in the Science Museum. I somewhat shocked the lady in the museum because I sat down, laid my hands on it and said, "This is the first time I've touched this in 44 years." And she hadn't realised it was the same one, but I'd traced its history, which wasn't difficult, and it had in fact ended up in the Science Museum. So that's rather nice. I went to Simon Langton Boys School from the Electronics Department at University of Kent, and they donated it to the Science Museum. I'm also looking at doing an emulator for the ICL 2900 range of machines. They did two sorts, the P series and the S series. The P series was the one that we had at Kent. We had a 2960, which was the lowest of the low of the P series. There's no reason why you can't do that as well. That will just be software. I can't see any. It had hundreds and hundreds of lights, and none of them meant all that much, actually, to be honest. So it wasn't. It's not really feasible or interesting to produce a box with lots of lights and switches. You pretty well did everything for an operator panel. But this is what a 2960 looked like. The operator panel was, you can see where the woman on the left is standing in front of. That's actually the engineer's panel. It has a little keyboard and a small screen with about a dozen rows of, I think, 20 characters. And that was what you used to actually start the machine, just by typing a couple of commands. And you could run tests on there as well. The tests were run from tape. They were compact cassettes, actual old compact cassettes, like the audio cassettes, but presumably higher quality tape. So the black cabinet immediately behind that screen is actually the engineer's panel. The three next to it are the CPU, and the box at the end is the store multiple access controller, which is essentially what connected that was the memory, and what connected the memory to the peripherals. The peripheral controllers are out of the picture. On the right you can see the top of a printer there, and then in front of that the operator control panel called the OPER, with the other woman sitting down, two screens, one keyboard which you can see in front of her, and some switches on the right which allowed you to stop and start various things. So I'm working on that. But yeah, it had several hundred lights, mainly inside the store box, that last one. And yes, I could get an idea from all the lights what was happening, but individually they didn't mean a great deal, and it wasn't really not really something you want to emulate. Well, that nearly brings me to the end of this, and it's gone slightly over the hour, but never mind. I've probably rambled on more than I would in public. But thanks again to Oscar for these wonderful kits. They're an absolute marvel. They're complete, they're well documented, they look good, and they're really faithful to the original, which is lovely. Thank you to him again for his agreement to use all these slides for part of this presentation. He was very, very nice to let me do that. I was only sorry I missed his talk in London, but I had an appointment that day I couldn't miss. Thanks also to Bob Supnick for all his wonderful emulation software on the PDPs. Thanks to Bob Armstrong. He's the guy who produced the SBC 6120, and it's a really nice design. And thanks again to John Todd. John Todd was the guy professor in the chemistry department who originally ran the mass spectrometer, and although he doesn't remember it, must have supervised Paul Berry when he was doing his stuff that I first saw, which got me interested in the PDP-8. And John Todd bequeathed me a load of PDP-8 documentation when he moved, and it's lovely to have that. So that's really good. So we come to the conclusion, and playing with old computers is instructive, it's fun, for a certain sad sort of person like me anyway, and really it is. But real old computers are hard to obtain, and if you can get hold of them on eBay or whatever, they probably don't work. You're probably going to have to do a lot of work, and it's going to cost you a lot of money. But if you're really enthusiastic, why not? You could build a replica computer. Some of the chips these days are hard to come by, but if you can build it from individual components, if you are so that way inclined, if you do that, you might want to go for the room full of computer if you want to do something silly. Emulation you can do entirely with software. SimH runs practically well anywhere, Windows, macOS, Linux and BSD as I say there, but I've run it on OS2 for example. It's a portable C program and it really should be no great trouble to get going anywhere. Emulation with display hardware, by which I mean, well, obviously the LEDs, but also the switches and things like that. It's nice, it does involve you in some financial outlay, but it's probably worth it for the nice aesthetics. So have a go at this, have a go at doing all these things, and perhaps let me know how you get on. Now in the original talk, of course, I was asking for questions, and that's not easy to do right here, so I'll skip over this slide and move to the next one, which tells you how to contact me. bob@eager.cx will find the find me, of course. The website, which has the slides as well as this, you probably found already, bobeager.uk. There's also a link on there to other things such as installing BSD Unix on a VAX, and how to do that in detail using SimH. The PyLP website, where you can order kits for the PyLP 8 and the PyLP 11 at the moment. And all the old documentation is pretty well available on bitsavers.org, so you can get all the original user documentation. So again, there's no worry there about not knowing how to do something. And that really does complete the whole thing. So thank you very much for listening. I hope you enjoyed it. I hope it wasn't too boring or too slow, but let me have some feedback.